Now the slides have vanished.
Yeah, shake the mouse maybe.
Oh, it was simple as that. Sorry.
Just the threat of shaking the mouse brought it back.
Oh, I just did use the. So I'm going to talk today about InfiniBand in-network computing, subject that's near and dear to my heart. Before I start, as folks probably know, we're at the HDR generation of technology. I believe it's just GA'd. If not, right now it's GA means become generally available. If not, it's within days. And here's a list of some of the larger systems that are publicly known in terms of using HDR technology. So TAC is probably the biggest one of the biggest known ones, and KMA is going to come up soon too with this technology. So now getting to more to a technical focus in the discussion. So to sort of frame the context for this discussion, when you build networks, build support for networks, of course you have to provide high bandwidth and low latency and scalability. Sorry. And high message rates and things like those. Those are sort of basic capabilities that without them, there's not much use for the network. So those are basic capabilities that everyone expects as networks increase in terms of performance. But that's only one. That's an important component, but only one component that determines the overall utility of the network capabilities. And so, when we look at adding new features to our next generation technologies, the concept that we look at how one of the things we look at is how we can improve overall system efficiency by adding compute capabilities within the network. That is not assuming that all computation will be done at the edge, but putting computation within the network in places that make sense to support capabilities that are frequently used. So this is really a prime motivator in terms of how we design our networks. So we tried, and it's a capability that will help scale up help us scale as systems get larger and larger. So from some of the easier targets to handle early on are so-called computational elements of communication libraries. That is, moving management of computation elements from the endpoints to the network itself, with a goal here of producing fairly large improvements in overall capability to support those sort of operations. So I've been talking here very vaguely. But some of the early targets, and some of you already have experience with these capabilities, is, for example, acceleration of collective communication, where you can, because of reduced data motion, because of getting software out of the way, improvements in latency can be significant, and I'll talk about a very specific case here early on. So that's one natural target. It's an easy target because they're well-known communication interfaces that are used by virtually everyone in HPC. Not everyone, but virtually everyone. You have MPI and OpenSHMEM, for example. And so it's really not, in terms of picking elements to optimize, it's not quite as difficult a task. The other thing that we're starting to do now is with our smart NICs, we're giving the ability to do computation within the network device itself, giving the application the ability to do computation within the device itself. And so the goal there is not to compete with the CPU, because if you want that computational power, just buy more CPUs and do it there. But the goal here is more to take advantage of the fact that in distributed algorithms, in when you send data to storage, when you're sending data for some sort of analysis and the like, the data is moving anyhow, and you might as well you have an opportunity to deliver something that's more of a finished product, something that can be used immediately rather than have to be processed at the end nodes. And so that's one of the areas that's being investigated now with these new devices called blue fields. So I won't talk about blue fields today, but I wanted to get that in there because this is an area that at least to several people in the room here is very interesting. And so it's an area we're trying to understand what makes sense to do there. So from a system design, from a system perspective, the work that we do in this general area really goes into several different falls into several different categories in the end-to-end stack, communication stack. So we do work at the system level in terms of determining connectivity. This might be ways to improve the utilization of the network capabilities using technologies such as multi-host or socket direct, which allows a single device to be able to support communication capabilities from more than a single host or more than a single socket. And so if your single source of data doesn't need the high data rates that are available today, you can share those capabilities can be shared between multiple hosts, and making the interior portion of the network cheaper. That is, you don't have to have as many switches and the like, so that it makes the system more cost effective. There's also work that's done at the network level, so on the cards and in the switches. Of course, the network transport itself has been offloaded since day one. I mean, that's the way Mellanox has been designing the network support for the last 20 years. Capabilities such as RDMA and RDMA direct, GPU direct RDMA, sorry. Shield, which I'll talk about, is a capability for the network repairing itself or dealing with errors with problems in the network. Adaptive routing, congestion control, and those sort of things. At the communication level, I already indicated the fact that we do offload various elements of communication stacks. And the MPI is obviously the major target since it's the one used most. We have SHARP for accelerating collectives, and I'll talk about that. We have support for MPI tag matching, intended to provide asynchronous progress and computation overlap, and the ability to define virtual software devices. So what I mean here, the simplest example to give here is those of you that use storage, use NVMe, use the NVMe capabilities. We have in our device the ability to, in our ConnectX-6, the ability to translate an NVMe request to an NVMe over Fabric request, and so those users so users don't have to change their storage code or whatever to gain the ability to access remote NVMe devices through the NVMe interface. So it's and then we also do work at the application level. The goal of this work is really to, at the end, is to improve application performance. I mean, this is why New features are designed. This is why we go and try and work with customers and other people to understand their codes and help them improve application performance. This is the only application example I think that I'll give today. This is very recent work that we did on a code called ICON with DKRZ. It's a weather simulation code. My understanding, it's starting in a year. It will start to become the production day-to-day weather code in Germany and later in Switzerland, and I guess more than that. So in this particular code, what we did here is this is a three-way partnership with DKRZ, who own the code and know the code and can help in terms of understanding the characteristics of the code. University of Tennessee Knoxville was also involved. They were involved because the major changes that have gone in so far have gone on the MPI side of things, to Open MPI, and so we made changes to MPI's data type to be able to optimize the halo exchange that ICON was doing. And so we needed them and their expertise to help here. And what we did basically was sat down with DKRZ to understand their code characteristics, not to look at MPI profiles, because MPI profiles a lot of times won't show you really what's going on. And in this case, what was done, DKRZ did this portion of the code, is they took their halo exchange, and instead of packing the data on their side, in the application level of the code, where it's invisible to the communication library, they expose it via the MPI data types mechanism. MPI data types optimize, recognize and set up a new data type description, which made the data packing, which made it possible to have a much more efficient data packing scheme. So at this stage, most of the optimizations have nothing to do with the network, just have to do with better use of resources available. But that's the first step. The second step is to use the hardware scatter-gather capabilities that we have in our network to further improve on application performance. So we want a realistic assessment of the benefits to the application here. And so we ran one of what's considered a production grade run this is actually run on DKRZ's system, 256 nodes, and there was a 16% improvement in overall ICON performance. So this is not, if you look at the communication piece, it was much larger, but this was just application performance side of things. It's something that we couldn't have done on our own because it would have taken us years to learn the code. But together we were able to do this work, and so this is the sort of direction we like to take. So now let me get to some of the features that are part of in-network computing. The first one that I'll talk about is SHARP, Scalable Hierarchical Aggregation Protocol. The point of this technology is the technology, the SHARP technology that's available today, is to optimize reduction operations. So think of your barriers, think of your reduce, AllReduce. We actually have support for broadcast now because it has similar capabilities that are necessary to implement reduce and AllReduce. And there are some other collectives that are also fall into this category. And so what's done in this technology was developed with NRE as part of the Coral project, and it supports all the collective communication primitives that are defined by MPI. And by SHMEM. There's one exception, which is the reduction. Actually, there are two exceptions. One is the multiply operation is not the multiply reduction operation is not supported. It's very, very rarely used, and the user-defined reduction operations also aren't supported. We don't know how to generalize that in a way that makes sense. And so the key idea here is that basically one builds a reduction tree within the switch fabric. We have a switch fabric here that looks like this is basically a fat tree, but it's not restricted to that by any means. The network topology does not need to be a fat tree at all. But a reduction tree is built within the fabric, and reductions are performed over that reduction tree. So there are a couple things a couple of features of the network that make this very efficient. So one, with a host-based operation, you typically send data into the network multiple times. This is if you have a small data reduction, you do some sort of logarithmic operation. If you have a large data reduction, you do some sort of linear operation, injecting data into the network n times, where n is the number of participants in the reduction operation. Here each host injects data into the network once. And the network radix is very large, so at every step, the amount of data that comes in that leaves that node is 1 over the radix of what came in. So there's very good network utilization. You really collapse. You really send a minimal amount of data around. The result gets to the root of the operation, which then distributes it back down the tree. So actually, an interesting thing to note. I don't know how many of you have seen the GPCnet benchmark recently that Cray put out. So SHARP is completely insensitive to noise at the sizes that were measured. It's really isolated from the rest of the system, which is really one of a huge benefit for this, because it really doesn't inject a lot of data into the network, relatively speaking. So the data that we have right now is for short reductions. I have a figure here of the latency for AllReduce for 8, 128, 1K, and 2K bytes. A couple key things to solid lines are the latencies that are due to for the algorithm when you use SHARP. The dotted line here is the latency of algorithms used with an endpoint-based or host-based algorithm. Actually, it's optimized. It does use hardware multicast to also accelerate it. But the point here is it's a comparison to a very well-optimized reduction operation. So the first thing we see is that latency is improved dramatically with using SHARP versus using an endpoint-based approach. So here the difference is about a factor of 2.1. When you get to 128 nodes. The other thing is you'll notice that latency is almost flat. There's a knee here in the curve, and this is when you go from using one switch in the reduction to three switches. It becomes a two-level tree. And the major cost here that you pay is really the number of times you go through the switch. That's where the main cost comes. The radix of the actual radix of the operation really doesn't impact latency very much. It does, but very, very little. Not visible here. So here's some data on larger systems. This is on system. This is measured on the University of Toronto system, 1,500 nodes. MPI AllReduce for it's plotted as a function of message size from 8 bytes to 2K, 1 process per node, and full PPN. This is a 40 processes per node system, and so again we see even better performance improvement on that system. So if I remember correctly, performance improvement here is on the order of a factor of 5 or so. So really big performance impact on the reduction operations. Now, one thing to mention here too, so people have the right expectations here, just like on any system, if you don't use the resources well, you get what you get in terms of mileage. So collective operations generally are sensitive to load balance. So if you have a large load imbalance, a lot of these benefits are hidden. If most of the time you're waiting for one outstanding process to come and contribute its portion to the reduction, that will, what you see at the application level will be less than what you'd see in a primitive benchmark that shows the capability. So this reduction support works extremely well for machine learning, since a very big component of machine learning, a lot of time is spent in doing the vector reduction to gather the parameters. So this is ideally suited for that. Actually, in our HDR capability, with our HDR switches, we've added the ability to reduce long vectors, and so there, the bandwidth that's observed in reduction is on the order of 80%, 80 to 90% of line rate, and so we do have some we do have some work that we've been doing with NVIDIA on nickel, and so NVIDIA uses SHARP for their in nickel, in their nickel library. And we have here the bandwidth measured with nickel using 1 HCA, 2 and 4 HCAs between nodes. If I remember correctly, it's a four node, four nodes, 32 GPUs are used here. We see it going from okay, I'm sorry. This is the performance of nickel with using their tree algorithms, better performance using the ring algorithms, which are more optimized, and then when SHARP is used, using the network within the reduction, there's even a large improvement, in performance, getting up to 70 gigabytes per second observed bandwidth. In terms of how this plays out in AI, there's performance data here for the ResNet 50 training run. On 8 nodes, 16 GPUs. If SHARP is used, there's an 11% improvement in overall training time, and on 8 nodes, it goes up to 16%. So there's quite a bit collaboration has been done recently to continue and improve the performance. Here. I'm sorry, I'm lost track. Yeah. So quality of service is another element of support that we have within the network, and there the notion behind quality of service is you can define different categories, different service levels, and put traffic within those service levels. From a resource perspective, each service level has its own resources in the switch, and so there's no resource contention between at the switch level. There's no resource contention between elements from different virtual lanes. From a scheduling perspective, higher priority traffic is scheduled before lower priority traffic. And so this works really well. You can see higher priority traffic really goes through the network with as though there's no other traffic in the network. But of course, it impacts the lower priority traffic because it gets lower priority and it isn't sent as fast. So this is used mostly to sort of put storage on one traffic lane, one traffic level, one virtual lane, applications at another. NVMe uses this, for example, to put its priority down really low, so it won't interfere with other communication from applications on the network. Actually, it does that along with some rate limiters that are used So this is a capability that works really well. In principle, you could use it within an MPI, but the means of doing that is the MPI, the interface does not expose these sort of capabilities very well. Congestion control has also been in our fabric for about 7 years. When I joined Mellanox about 7 years ago, it was a really hot topic, but didn't seem to get much traction with customers. Didn't seem to care about it too much. Bottom line, congestion control is a capability in the switch to detect congestion and use that to modify traffic patterns. Without congestion control, you have there are several different traffic patterns that are shown here. Red is the traffic pattern that started first. It's considered the victim traffic. You can see they share a common link. So this is where there can be interference from other traffic in the network. And without going into details, without congestion control, as soon as other traffic starts to come, as you would expect, network utilization starts to go down, you get congestion spreading and the like, which causes things to go worse. If you turn on congestion control, the impact on this red flow becomes much smaller. So it's there, it works. We haven't been using it on the InfiniBand side of things. On the data center side of things, on Ethernet, it's used a lot. It's in very high demand. It's very much required. And so right now, we're actually in the process of activating what we use in InfiniBand for our IB, because Cray came out with a benchmark that sort of forced everyone to start looking at that, and so we're doing that. Another capability that exists in our hardware is called Shield. Shield is a way to deal with errors in the network. When data is sent through the network, it has a default path that it goes through. In this particular case, we're sending data from server A to server B, and this happens to be the route that it would take by default. If along the route something happened at a switch and the route becomes unavailable. So maybe a cable went bad, a port went down, who knows what happened, but data is no longer able to go here. And so with the default routes, this data would be stuck. You would have nothing to do. You would have to actually not manually. The subnet management would wake up, detect the problem, would be notified of the problem, change the routing tables. And then things would continue. And that takes, on a system that's not too large, it could take a second, 2 seconds, a while, enough to cause problems at the application level. However, at this level in the switch, there are still alternative paths, and there can. So this shield capability, what the shield capability does is gives you the ability, when you hit this sort of problem, to choose another path. And so here the decision is easy. Because there's another path locally here, so it just routes the data through another port, and it gets to the destination. However, if you get to a case where when the error is detected, there's no alternative route, you're stuck, right? You can't make a local decision to do something else. And so what Shield does is it basically sends information back through the route about the failure until it reaches a point where a new decision can be made locally, and at that point the new route is taken and the data is delivered. So this recovery takes on the order of milliseconds versus seconds or more before this capability was added, and so. Yeah, the network, that particular traffic will stall for a few milliseconds, I'm sorry. But the stall is not bad enough that it makes the application fail. And so if you look at the difference in time, it's about a factor of 5,000 or so. So that's why we talk about a 5,000-fold improvement in performance there. But it's useful. We've used it actually when HDR bring up. It was very useful. Early on, hardware has problems that you need to figure out what they are, and so that was very useful there. We also support adaptive routing. I'm running out of time, so I won't talk about it much here. for those of you that don't know, adaptive routing is basically uses the ability to choose alternative routes based on network traffic load. It's different than congestion control. This really deals with spreading traffic throughout the network, as opposed to dealing with congestion control. You deal with traffic where you have no alternative routes. Here you have alternative routes, and the alternative routes are selected. So Los Alamos did some measurements on the Summit system without using an all-to-all type of data pattern. Measured the bandwidth obtained for the different data exchanges, and got this distribution of network utilization, which corresponds basically to how many pairs are sharing a given link. When they turn on adaptive routing, the adaptive routing spread the traffic in such a way that those shared links were no longer a problem, and all traffic is getting on the order. I think, if I remember correctly, has peaked around 96% of network utilization. So the last slide is just to talk a bit about HDR, which is our latest product to come out. This includes the ConnectX-6 switch, the the ConnectX-6 adapter, the quantum switch, version of Bluefield, and some other cable support, as well as software. So ConnectX-6. The technology as a whole runs at 200 gigabits per second. ConnectX-6 has the latency for this device is 0.6 microseconds, so no change from ConnectX-5. Slight increase in message rate to 215 million messages per second from 200 that existed at ConnectX-5. It's backward compatible. It introduces a new capability that we didn't have before, where we will use two lanes of data over the network to form a single stream of data. And what I mean here is we have support for HDR, which is 200 gigabits per second, but we can also support through the same cable 2 streams of HDR 100. So they're and we take advantage of that at the switch, where we can, on a port-by-port basis, decide if a port is supporting HDR or HDR 100. And so the radix of the switch, if all the links are at 40 at full gigabit, 200 gigabit per second, it's a 40 port switch. If all the ports are split to 2, it will be an 80 port switch. So we're seeing quite a few people using HDR 100 from the nodes to the switch, and then using the HDR between nodes, which really helps cut down on the cost of the infrastructure. The other part of this portfolio is the Bluefield adapter. It's a smart adapter that has ARM programmable ARMs on the device running Linux as the operating system. We actually have probably at least half a dozen different projects in the area of HPC trying to figure out how to use this for HPC applications right now. And so this is an active area of work. And as a matter of fact, the Iraq program is actually supporting some of this work here. LinkX, we have the cables that go along with to support this, and as always, we use HPCX as our quickest way to expose these capabilities to the users through MPI, OpenSHMEM, UPC support. So that's all I have.